So this is the very first question for this series. The question is from the digital subject as a topic Boolean Algebra, and the question here is the Boolean expression under bracket x plus y into under bracket x bar plus y into x plus y bar into under bracket x bar plus y bar bracket close simplifies to option A x, option B y, option C 1, option D 0. Now the next question is the expression x bar y bar z plus yz plus xz simplifies to option A x bar z, option B z, option C 1, option D 0. Now the next question is consider the following Boolean function f is equal to a bar b under bracket d bar plus cd plus c bar d bracket close plus b under bracket a plus a bar cd bracket close full stop. The simplified expression up to the minimum number of literals is option A f is equal to a, option B f is equal to a bar c, option C f is equal to b, option D f is equal to a bar b. Now the next question is which of the following are the correct relationship? Question mark. So option A XOR B whole bar is equal to a bar XOR with b, option B a bar XOR with b is equal to a XOR with b bar, option C a XOR under bracket b or with c is equal to under bracket a XOR b ORing with under bracket a XOR c, option D a XOR b bar is equal to under bracket a XOR b bar. Consider the Boolean function f is the function of xy is equal to under bracket x XOR with y ANDed with xy full stop. The minimum number of 2 input NAND gates required to implement this function is fill in the blanks. So the question here with the continuity of the series is consider the following function f is the function of a comma b comma c comma d is equal to b bar d plus a bar d plus bd, where a is MSB and d is LSB. It can be represented as option A f is equal to sum of the mean term under bracket 1, 3, 5, 7, 9, 11, 13, 15. Option B f is equal to sum of the mean term under bracket 0, 2, 4, 6, 8, 10, 12, 14. Option C f is equal to product of the max term 1, 3, 5, 7, 9, 11, 13, 15. Option D f is equal to product of the max term 0, 2, 4, 6, 8, 10, 12, 14. So the question here is a function is represented in sum of products, that is SOP form. So f is the function of x, y, z is equal to x plus under bracket x bar, y bar plus x bar z their whole bar. Their minimal product of sum, that is POS, is option A x plus y z bar, option B x plus y into x bar plus z, option C x plus y into x plus z bar, option D x bar plus y bar into x bar plus z bar. So the next question is if x and y are switching variable, comma, then x XOR with y XOR with xy is equivalent to option A x ORing with y, option B x XNOR with y, option C x y bar XOR with y, option D x XOR with x bar into y. So the next question is consider the function f is equal to x XOR with y XOR with z bar, comma, their sum of mean terms is option A f is equal to sum of mean term 1, 3, 5, 6, option B f is equal to sum of mean term 0, 3, 5, 6, option C f is equal to sum of mean term 1, 2, 4, 7, option D f is equal to product of max term 0, 3, 5, 6. Next, given the network having f1 is equal to x bar z plus x z bar and overall transmission function, so the function of wxyz is equal to, here it is given some of the mean term 0, 4, 9, 10, 11, 12, where w is MSB and z is LSB. So the network is given here. The functions f2 and f3 are respectively option A, f2 is equal to sum of mean term 4, 9, 11, 12, and f3 is equal to sum of mean term 1, 10, 11. Option B, f2 is equal to sum of mean term 1, 5, 11, 12, and f3 is equal to sum of mean term 10, 11. So option C, f2 is equal to sum of mean term 4, 9, 11, 12, and f3 is equal to sum of mean term 0, 10, 11. Option D, f2 is equal to sum of mean term 8, 4, 11, 12, and f3 is equal to sum of mean term 10 and 11. So the question here with the continuity of the series, consider the K-map given below. So this is the K-map given here. Prime implicant is represented by Pi and essential prime implicant is represented by EPI. Full stop. Which of the following are correct? Question mark. Option A, Pi is equal to 0. Option B, EPI is equal to 4. Option C, Pi is equal to 5. Option D, EPI is equal to 1. And the next is, consider the K-map given below. So the K-map is given here, and the minimal product of sum, that is POS expression, is option A under bracket y plus z into under bracket y bar plus z bar into under bracket w plus x into under bracket w bar plus x bar. Option B under bracket y plus z into under bracket w plus x into under bracket w bar plus x bar. Option C under bracket y bar plus z bar into w plus x into under bracket w bar plus x bar. Option D under bracket x plus z into under bracket x bar plus z bar into under bracket w plus x into under bracket w bar plus x bar. So the next, a contact network with 4 input relays W, X, Y and Z, which receives BCD numbers and produces a signal whenever the present number is 3 or a multiple of 3, full stop. The minimal sum product, that is SOP expression of this function, is where W is MSB and Z is LSB. Option A, F is equal to X, Y into Z bar plus X bar into Y into Z plus WZ. Option B, F is equal to Y into under bracket X XOR with Z plus WZ. Option C, F is equal to X bar into Y into Z plus X into Y bar into Z plus WZ. Option D, F is equal to under bracket X XOR with Y into Z plus WZ. Next problem is, consider a Boolean function given below. F is equal to A into B into C bar into D bar plus A into B bar into C bar into D plus A bar into B bar into C into D plus A bar into B into C into D bar. The sum of minimum number of XNOR gate and NOR gate required to implement the above function is, fill in the blanks. So the next problem, and this is the last problem for this day third. So the question here is, consider a Boolean expression f is equal to w bar into x into y bar into z bar XOR with w bar into x into y into z bar XOR with w into x bar into y bar into z, where number of literals is denoted by p and number of literal count is denoted by q, full stop. The minimum of p, q required to express the above expression is option A 7, 7, option B 12, 7, option C 7, 12, option D 12, 12. So the question here is, consider the Boolean function. So f is the function of xyz is equal to xy plus x bar into y bar plus yz bar, full stop. The minimum number of 2 input NAND gates required to implement this function is, fill in the blanks. Next, consider the logic circuit given below. So this is the circuit given here. The simplified expression for f is option A xy plus x bar into y bar plus yz bar, option B x XOR y bar plus y bar z, option C x XOR with y plus y into z bar, option D under bracket x XOR y plus yz bar. Next, Consider a Boolean function f is equal to x y z bar plus x y bar into z plus x bar z, comma, their simplified equivalent realization is. So these are the circuit given in these all the four options, so you need to take care about this. Next, consider the logic circuit given below. So this is the logic circuit here. The equivalent expression for f is option A x naught under bracket BC plus D, option B A XOR under bracket BC plus D bar, option C A bar XOR under bracket BC plus D, option D A bar XNOR under bracket BC plus D ka bar. So the next, a Boolean function is given by f is equal to a bar into b into c bar into d bar plus a into b bar into c bar into d bar plus a bar into b bar into c bar into d plus ab into c bar into d. So here it can be expressed as option A XOR B XOR C XOR D. Option B under bracket A XOR B XNOR under bracket C XOR D. Option C under bracket A XOR B XOR D bracket close into C bar. Option D under bracket A XOR B XOR C bracket close into D bar. And now we are going to start with the combinational circuit. So the question here is, given a combinational network with three inputs x, y and z and two intermediate outputs p and q and final output f. So this is the circuit given over here. To realize the above function, the logic gate G is option A either XOR or XNOR, option B XNOR only, option C either AND or option D XOR only. Next. So the next is, a Boolean function is realized by the block diagram shown below with three inputs x, y and z and output f. So the network is given here. To realize the function f, the logic gates G1 and G2 are so and so respectively. Option A AND, OR, option B XOR, AND, option C NAND, NOR, option D XOR, XOR. Next, the question here is, figure below shows a two-way switch which is mainly used in home and hotels to turn on the light. So the circuit is given here. To glow the LED, the required conditions are option A is equal to 0 and B is equal to 0, option B A is equal to 0 and B is equal to 1, option C A is equal to 1 and B is equal to 1, option D A is equal to 1 and B is equal to 0. So the next, a multiplexer is realized by multi-inputs NAND gate only. The minimum number of multi-inputs NAND gate required to realize 16:1 mux is fill in the blanks. Next, a half adder and half subtractor is shown below in figure. So this is the figure here for the half adder, for the half subtractor. The half adder of figure 1 is cascaded with half subtractor of figure 2 as shown in block diagram. So this is the block diagram here. The expression for F1 and F2 are option A, F1 is equal to A XOR B and F2 is equal to A bar into B. Option B, F1 is equal to A XNOR B and F2 is equal to A into B bar. Option C, F1 is equal to A plus B and F2 is equal to A into B. Option D, F1 is equal to A XOR B and F2 is equal to A into B bar. So the question here is, consider the combinational circuit given below. So this is the circuit given here. The equivalent expression of F are option A bar plus B bar plus C, option B A plus B plus C bar, option C under bracket A plus B plus C overall bar, option D under bracket A bar into B bar into C and their overall bar. So the next, consider a 3-bit relative magnitude comparator. So this is the block diagram for this relative magnitude comparator. The number of input combinations for which A is greater than B, it means Y is equal to 1 is fill in the blanks. Next, a half adder is made up by the use of XOR gate and AND gate only as shown in figure. So this is half adder. To implement the following two Boolean expression, P is equal to A XOR B XOR C, Q is equal to A bar into B into C plus A into B bar into C, the minimum number of half adder required is fill in the blanks. Next, consider the logic circuit given below. So this is the logic circuit here. The required input conditions to make the output x is equal to 1 is option A is equal to 0, B is equal to 1, C is equal to 0. Option B, A is equal to 1, B is equal to 0, C is equal to 0. Option C, A is equal to 0, B is equal to 0, C is equal to 0. Option D, A is equal to 0, B is equal to 0, C is equal to 1. Next, a half adder is connected to a 4:1 mux as shown in figure. So this is our mux and this is half adder connected as shown in this block. The simplified expression for f is option A, f is equal to A XOR B, option B, f is equal to A XOR B, option C, f is equal to A plus B, option D, f is equal to A into B whole bar. And now we are going to start with the sequential circuit. जैसा कि हम सब जानते हैं कि डिजिटल सब्जेक्ट में सीक्वेंशियल सर्किट बहुत ही ज़्यादा इंपॉर्टेंट होता है विथ रिस्पेक्ट टू गेट एग्जाम और यहाँ से मोर फ्रिक्वेंटली क्वेश्चंस पूछे जाते हैं। तो यहाँ पे मेरा छोटा सा सजेशन है कि आप ये सारे प्रॉब्लम को प्रैक्टिस करने से पहले आप इस टॉपिक का अच्छे से वहाँ पे रिवीजन कर ले एज लाइक हमारा फ्लिप फ्लॉप, लैचेस, रजिस्टर्स, काउंटर्स एक्सेट्रा, वो सारी चीज़ को अच्छे से पढ़ लेंगे तो ये सब आसानी से बनेगा और आप ज़्यादा से ज़्यादा इसको एंजॉय कर पाएंगे। So now the question here is a 5-bit binary up counter starts from the 0 0 0 0 0 state full stop after 144 input clock pulses. The count value of the counter in decimal is fill in the blanks. So the next, a 3-bit binary ripple counter uses T flip-flops whose all the inputs are high and initially normal output of all the flip-flops are reset full stop. If negative edge of clock is used to trigger counter flip-flops and complemented output of flip-flop is connected as clock to drive the next level of flip-flop, then the value of count in decimal after 5th clock pulse is fill in the blanks. Next, a NOR latch is shown in below figure. So this is our NOR latch. Assume each NOR gate is having equal and finite propagation delay of 2 nanoseconds and initially Qn is equal to 0 and Qn bar is equal to 1 full stop. At t is equal to 0, the inputs applied are x is equal to 1 and y is equal to 0 full stop. The minimum time under bracket in nanosecond after which stable outputs are produced is equal to fill in the blanks. So the question here is for the modified ring counter shown in below figure, assume that initially Q0 is equal to 1, Q1 is equal to 0 and Q2 is equal to 0. So this is the figure given here. The number of clock pulses required to reach the initial state again by completing their cycle is fill in the blanks. Next, consider the cascading of counters shown in below figure full stop. Assume that all the outputs initially reset. So this is the figure here. The duty cycle of Q3 is fill in the blanks. So the question here is for the logic diagram of the synchronous counter shown in below figure where Q2 is MSB and Q0 is LSB. So this is the figure here. Initial value of Q2 is equal to Q1 is equal to Q0 is equal to 0. Modulus of the counter is fill in the blanks. Next, a 2:1 digital multiplexer having a switching delay of 1 microsecond is connected as shown in figure full stop. The output of the mux is connected as input clock to the 2-bit ripple counter full stop. Initially, all the outputs of the counter QA is equal to QB is equal to 0 and all the inputs of T flip-flop are high. So this is the figure given here. The frequency at QB under bracket in kilohertz is fill in the blanks. Next, a synchronous counter is designed by the use of positive edge triggered T flip-flop full stop to achieve the counting sequence 0 to 2, 2 to 1, 1 to 3, 3 to 0 and so on. The required connection is under bracket where Q1 is MSB and Q0 is LSB bracket close. Option A, T1 is equal to 1 and T0 is equal to Q1 bar. Option B, T1 is equal to 1 and T0 is equal to Q1. Option C, T1 is equal to 0 and T0 is equal to Q1 bar. Option D, T1 is equal to 0 and T0 is equal to Q1. Next, consider the sequence detector state diagram given below. So this is the state diagram given here. starting at the state S0, that is reset state. If the input is given as 1 1 0 triple 1 0 1 1 0 under bracket, input is given from left to right bracket close serially, then the number of times S2 is traversed is fill in the blanks. Next, so the question here is a D flip-flop is required to change into JK flip-flop full stop. The required logical expression to make the change in D flip-flop into JK flip-flop is, so this is the D flip-flop given here. Option A, D is equal to J into Qn plus K bar into Qn. Option B, D is equal to J bar into Qn plus K into Qn bar. Option C, D is equal to J into Qn bar plus K bar into Qn. Option D, D is equal to J bar into K plus J into K bar. In a certain number system, an arithmetic operation is performed like under bracket 302 by 20 under base y is equal to under bracket 1 2.1 under the base y. The value of y is fill in the blanks. So the question here is, in the following series the same integer is expressed in different number system 1 4 times 0 comma 1 to 1 comma 100 comma question mark comma 24 comma 22 comma 20 and so on. The missing number as a question mark of the series is option A 15 under the base 5, option B 31 under the base 5, option C 15 under the base 6, option D 31 under the base 6. Next, the question here is, consider two binary number x is equal to 1.10010 and y is equal to 110.010 is used in some arithmetic operation. Z is equal to y by x, comma, then the value of z is fill in the blanks. Next, so the question here is, using the sin 2's complement representation and enough digits to accommodate the numbers full stop, let x is equal to under bracket plus 29 plus under bracket minus 49, then the result of x is equivalent to option A under bracket 1101100 under the base 2, option B under bracket 754 under the base 8, option C under bracket 1110100 under the base 2, option D under bracket EC under the base 16. So the next, the question here is, the state of a 12-bit register is 1 000 1 00 10 111 full stop. It represents option A 897 in BCD, option B XS3 code of BCD 564, option C under bracket 4227 under the base 8, option D under bracket 8A7 under the base 16. And the question here is, consider an 8-bit binary weightage resistor type DAC under bracket digital to analog converter full stop. If the resistor value corresponds to MSB switch is 1 kilo ohm, then the resistor value under bracket in kilo ohm corresponds to the LSB switch position is fill in the blanks. Next, consider an 8-bit counter type ADC under bracket analog to digital converter which is operated at 1 MHz clock frequency, then their maximum conversion time is fill in the blanks microsecond. Next, consider a 4-bit DAC whose one of the input is stuck at 0 and remaining inputs are connected through output of 3 bits freewheeling ring counter full stop. Initial output of ring counter is assumed Q2 is equal to Q1 is equal to 0 and Q0 is equal to 1 and resolution of DAC is 5 millivolt. So this is the block diagram given here. The output under bracket V out after 7th clock period is fill in the blanks millivolt. Next, an 8-bit DAC has a full scale output of 15 volt. Then the output for an input of 11001010 is fill in the blanks volt under bracket up to 2 decimal places. Next, Consider a 4-bit successive approximation ADC in which DAC is a part of ADC whose output is denoted by VAX, that is DAC output, and their corresponding waveform is shown in figure. So this is the waveform here for VAX. The clock is activated at time t0. Then by the end of one cycle of operation, the digital output of DAC is option A 1 0 1 0, option B 1 0 0 0, option C 1 1 0 0, option D 1 0 1 1. Consider the CMOS circuit implementation given below full stop. The equivalent expression is option A y is equal to under bracket A plus B into C plus D and their overall bar. Option B y is equal to under bracket A plus B into C plus D. Option C y is equal to under bracket AB plus C into D their overall bar and their again overall bar. Option D y is equal to under bracket AB plus C into D and their overall bar. Next, consider the circuit shown in figure full stop. The logic gate implemented by the circuit is under bracket assume diodes are ideal bracket close, option A and option B NAND, option C or option D NOR. Next, which of the following statements are correct with respect to CMOS logic family? Question mark. Option A, CMOS consume extremely low power in static state. Option B, dynamic power dissipation in CMOS depends on VDD and frequency. Option C, power dissipation in CMOS is inversely proportional to frequency of operation. Option D, dynamic power dissipation in CMOS is directly proportional to a square of VDD. Next, consider the circuit shown in below figure, comma, assume all the diodes are ideal and logic 0 is referred as 0 volt and logic 1 is referred as plus 5 volt, full stop. The logic gate implemented by the circuit is option A NAND, option B AND, option C OR, option D NOR. Next, which of the following are correct with respect to noise margin in logic family? Question mark. Under bracket, notations are having their usual meaning. For example, VNH denotes high state noise margin, full stop. Option A, VNH is equal to VOH mean minus VIH mean. Option B, VNH is equal to VIH mean minus VOH mean. Option C, VNL is equal to VIL max minus VOL max. Option D, VNL is equal to VOL max minus VIL max. So the question here is, consider the following Boolean functions. F1 is equal to A into B bar plus A into C plus A bar into B into C bar, and F2 is equal to A into C plus B into C is realized by the use of programmable logic array, that is PLA, full stop. The number of buffer inverter, comma, AND gate and OR gate are so and so and so respectively, full stop. Option A 3, 4 and 2, option B 2, 3 and 4, option C 4, 3 and 2, option D 2, 4 and 2. Next, so the question here is, consider the following Boolean functions. F1 is the function of x, y, z is equal to sum of mean term 1, 2, 4, 7, and F2 is also the function of x, y, z is equal to sum of mean term 3, 5, 6, 7. The size of PROM required to realize the above function is option A 3 by 2, option B 2 by 3, option C 8 by 2, option D 2 by 8. Next, so the question here is, a PROM is specified as 4K by 8, comma, the size of decoder required to implement this PROM is option A 10 by 1024, option B 12 by 4096, option C 8 by 256, option D 10 by 4096. Next, so the question here is, consider the programmable logic array, that is PLA, shown in below figure full stop. The function f is expressed as, so the circuit is shown here, and option A, f is equal to sum of the mean term 1, 2, 3, 7. Option B, f is equal to product of max term 1, 3, 5, 7. Option C, f is equal to sum of mean term 0, 3, 4, 7. Option D, f is equal to product of max term 0, 4, 5, 6. Next, so the question here is, a dynamic RAM, that is DRAM, is configured in such a way that it has 7 address lines in column wise as A0 to A6 and another 7 address lines in row wise as A7 to A13 full stop. The capacity of the DRAM to store the maximum information is, fill in the blanks, kilobits.